In this video, we will talk about marginal revenue and marginal profit. So I'm going to begin by defining the marginal revenue and marginal profit functions. So we say that the derivative of derivative of revenue, r prime of x, is called the marginal revenue function. And p prime of x, the derivative of the profit function, is called the marginal profit function. So these two things, the derivative of r and the derivative of p, they approximate they are the approximate revenue and profit from the sale of one more item after the xth item. So we had a really similar definition for the marginal cost function in the last video. Alrighty, so let's do an example. So blue books sell for 85 cents a copy. The cost of x copies to the student store is C of x equals 20 plus 0.05x plus 0.002x squared dollars. In part A, it's asking for what values of x is the marginal profit 0. Okay, so the marginal profit using this marginal profit function is p prime of x. So we want to set p prime of x, the derivative of profit, equal to 0. So to set that derivative of profit equal to 0, I'm going to need the profit function. So we're going to need to get the revenue and the cost. Alright, so let's begin with the revenue, because we already have the cost function. So the revenue, well, it tells us that blue books cost 85 cents a copy. So we would multiply that price in dollars, so that's $0.85 times the number of items, so times x. So this is coming from the fact that they cost 85 cents each. 85 cents each. Maybe a better word is the price is 85 cents each. Just because I don't want to confuse this quantity, the 85 cents, with the cost function, because the cost function is the cost to the student store. This represents sort of the cost to the customer, which is a different thing. All right, so the revenue function, we have that. So the profit function is revenue, r of x, minus the cost function, minus c of x. So if we plug into this, the revenue is 0.85x minus the cost function. So the cost function, I'm going to have to put it into parentheses, so I don't forget to distribute the negative sign to all the terms. The cost function was 20 plus 0.05x plus 0.002x squared. So distributing that negative sign and simplifying this a bit, we would get the highest degree term. Maybe let's write that in front. We'd have negative 0.002x squared. And then when we do 0.85x minus this 0.05x, we'll get plus 0.8x. So the 0.8x again is coming from this term and this term being subtracted. And then we have the minus 20 still. So the minus 20, that comes from distributing the negative sign to the 20. All right, so we have the profit function, which means we are now ready to take the derivative. So the derivative, p prime of x. So using the power rule, the 2 comes down, it'll multiply negative 0.002 and give negative 0.004, and then I have x to the 1 because I subtract 1 from the exponent. So my exponent will be 1. And then plus, so the derivative of 0.8x is just 0.8, and the derivative of negative 20 is 0 because it's a constant. All right, so this p prime of x, this is our marginal profit function. So we have our marginal profit function, so now we set this equal to 0. So now let's set negative 0.004x plus 0.8 equal to 0. And rearranging, we get 0.8 equals if I move the 0.004 term to the right, we get positive 0.004x. And then if I isolate x, we get x equals 0.8 divided by 0.004. And then I could simplify this. Let's rewrite everything as a fraction. So 0.8 is 8 over 10, and then 0.004 as a fraction would be 4 over 1,000. And this is something I could definitely do without a calculator, so I want to practice doing it without one. So 8 over 10, and then when I divide by a fraction, that's the same thing as multiplying by the reciprocal. So I multiply by 1,000 over 4. Okay, and then the 10 and the 1,000 cancel a little bit. I'll be left with a 1 here and a 100 up here. And the 4 and the 8 cancel a little bit. I'll be left with a 1 here and a 2 here. So finally, 2 times 100 is 200. So that's my value of x. That makes the marginal profit be 0. So what are the units of x? Well, x represented the number of blue books. So I need to include that. So whenever we have units, we should include those. And that's my answer. When the student store sells 200 blue books, that's when their marginal profit is 0. All right. So now I want to continue this example and talk about how we find where a function is increasing and where a function is decreasing. Okay, so this is going to be part B of this example. So let's find the intervals where profit is increasing and the intervals where profit is decreasing. So I'm going to break this down into steps. But the key idea is to remember that a function is increasing when its derivative, in this case we're talking about profit, so when the derivative of profit is positive. So when p prime of x is greater than 0. And a function is decreasing when its derivative, in this case the derivative of profit, p prime, is negative. So when p prime of x is less than 0. So the first step to figuring out where the profit function is increasing and where it's decreasing is to find the x values where p prime of x equals 0 or is undefined. So where the derivative equals 0 or it's undefined. And the reason for that is these x values are places where p prime might change sign. So from positive to negative or negative to positive. Okay, so graphically why that's important to us is, so if I have a graph, if I have my axes, and let's say that this is the graph of p prime, of the derivative function. So let's say it starts off positive and at some point it touches the x-axis and it crosses it. And let's say that this value where it crosses it is negative 3. Okay, and let's say that there's one other number here. Let's say it's where 2 is. And at 2 there's an asymptote, vertical asymptote. And my graph does something like this. It goes down towards the asymptote. And on the other side it goes up towards the asymptote. And then it sort of flattens out and does this. Okay, so looking at this graph, let me also draw an arrow pointing this way. Where negative 3 is on this graph, and we said this is the graph of the derivative, p prime. At that point where negative 3 is, p prime of negative 3 equals 0. So when a function equals 0, so when its y value is 0, the function might change sign, and that happened in this graph. It changed from being positive on the left-hand side to negative on the right-hand side. But a function could also change sign at a value like 2, because at 2, p prime of 2 is undefined. So when there's a place like that where my function is undefined, my function could change sign, and that happened in this graph that I drew. It changed from being negative on the left-hand side of 2 to positive on the right-hand side of 2. And again, this is the graph of p prime, not the original function p. All right. So for our function, we've already found the values of x that made the derivative equal 0. So the value of x that made the derivative equal 0 was x equals 200 in our example. And if we look up to our derivative function, let's see, do I still have it here? Yeah, the derivative function was negative 0.004x plus 0.8. If we think about when it's undefined, so if we think about our derivative function, there's no value of x that makes that undefined. So when is it undefined? This is never for our example. Never for our example. The main situation where that might occur is if we had a denominator in our derivative function, and then we'd think about what values of x make our denominator become 0, because that would make the derivative undefined. All right, so let's continue with this. So we are ready for step 2 now, which is to put these numbers on a number line and make a sign chart. Make a sign chart of p prime. Okay, so I'm going to start to make a number line. So I will make a number line. And on the number line, let's see, the only number that we got from step 1 was 200. So I put 200 as a tick mark on my number line. There was no other point that made the derivative 0, and there was no point at all that made the derivative undefined. There is one other value I'm going to put on my number line, and which is 0, and I'm going to put a bracket like this at 0. And the reason I'm doing that is because x, my variable, is a quantity. So x has to be greater than or equal to 0. So when I work with my number line, I only care about what's happening to the right of 0, or maybe exactly at 0, because x represents a quantity. That's the reason I'm putting 0 there. All right, so that's step 2, just making that number line. Step 3 is now we pick a test point in each what's called subinterval. So we pick a test point in each subinterval to plug into the derivative function. All right, so I'm going to begin by just copying my number line down. All right, so I just copied my number line down here, and let's talk about what these test points are. So the subintervals are the intervals that are between the numbers on our number line. So we have one subinterval from 0 to 200. So I'm going to pick a test point in that interval. It could be any number between 0 to 200. So I'm just going to pick something simple like x equals 1. Ideally, I want to pick something that's easy to plug into my derivative function. Remember, our derivative function here, p prime of x, was negative 0.004x plus 0.8. So I want something that's easy to plug into this derivative function. Let me write that p prime a little better. So p prime. So 1 seems like a simple value to plug in. And then I have another subinterval that's on the right-hand side of 200. So I might think, okay, maybe since I plugged in 1, maybe let's plug in 201. And I definitely could plug in 201. But ideally, it's nice to plug in values for which we don't need to use a calculator to do our computation. With 201, I will definitely need a calculator. Well, I mean, not for sure. I could work it out by hand, but it would be more tedious to do by hand. Something like 1000, though, would be really nice because I don't have to work that out. It's not as tedious to work out. That's what I mean. All right, and I don't need to plug in anything to the left of 0 because our variable can't be less than 0. It was a quantity. All right, so now what we do is I'm going to draw some vertical lines at these numbers that are on our number line, and I'm going to make a sign chart. So I'm going to make a row where I write down p prime, and I'm going to write a row where I keep track of what p sort of looks like. So what I'm going to do is I'm going to plug these test points into the derivative. That's what step 3 says. So p prime of 1, let's keep this in gray actually. So p prime of 1 is negative 0.004, and you plug in 1 for the x, plus 0.8. And if we work out what this is 0.796. So that one's not too bad. And if we plug in 1,000 into the derivative, we would get negative 0.004 times 1,000 plus 0.8. And if I multiply a number by 1,000, it moves the decimal point over 3 spaces to the right. So that'll give me the number negative 4, and then plus 0.8. And adding those, we get negative 3.2. Alright, so when we plug in 1 into the derivative, we get a positive number. When we plugged in 1,000 into the derivative, we got a negative number. So our last step is, now we write down where the function is increasing and decreasing. So write the intervals of increase and decrease. So when the derivative is positive in this first subinterval, that means our original function p is increasing. So the graph of p would be like this. It would be going up. And when the derivative is negative, like it was in the second subinterval, the original function p is decreasing. And that means our function is going down like this, from left to right. And conceptually, why this makes sense is, when the derivative is positive, the slope of the tangent line should be positive. And that corresponds to a graph that is increasing like this. And when the derivative is negative, the slope of the tangent line should be negative. And that corresponds to a graph that is decreasing like this red one was. All right, so now we are ready to write down the intervals where this is increasing and decreasing. So p is increasing on the first subinterval, so that's from 0 to 200. And remember, our convention is to use open intervals when we write down intervals of increase and decrease. So 0 to 200, keep it open. And then p is decreasing on the other subinterval. So that was starting at 200 and going onwards to infinity. And again, I use open intervals. And that is my answer, where my function is increasing and where my function is decreasing. All right, so one thing I'm going to note about the example we just did is, since our function p is increasing for all values of x that are less than 200, and it is decreasing for all, let's write that a little bit, decreasing for all values of x that are greater than 200. That means that p is, if we think about what that means intuitively about our graph, it's increasing everywhere before 200, increasing for all the values up till 200, and then it's decreasing everywhere after that. That means at this point, that's where x equals 200, our function is maximized. Our function, let me write that better, maximized at x equals 200. One of the ways to check where a function has its biggest value, where it's maximized, is if it increases for all the values up to a certain point, in this case 200, and it decreases for all the x values after that point, then wherever that point is, that has to be where the maximum value of our function is. We'll talk about maxes and mins more in chapter 5. We'll see this more in chapter 5. That's going to be one of our main applications of calculus, especially to business and econ problems, trying to find the maximum of something or trying to find the minimum of something. Trying to optimize a function under certain conditions is a really relevant problem. Okay, so what does the graph of our function p of x look like? Well, this one's a quadratic function, and a quadratic function has a parabola graph. And for this particular quadratic function, it is downward facing because the leading coefficient is negative. And I can see that the y-intercept is going to be negative 20. So the y-intercept is going to be negative 20. And in terms of what we now know the graph looks like, we know that this parabola, this downward facing parabola, we know where it has its max. We know that its max occurs at 200, according to the observation that we just made above. So why that's going to be useful to us, making this observation, is there's going to be a way for us to find the max and the min of a function without just using the vertex formula. And that'll be helpful if my function isn't a quadratic. If it's not a quadratic, we'd like a way to find maxes and mins, and we'll use the derivative to get them. Okay, so that was the graph of my original function. And that idea again, and we'll see this more, especially in chapter 5, is we'll use derivatives to find maxes and mins, which helps when the function is not quadratic. Alright, so I will end with one more example for this video. And that's a question about marginal profit. So this says the marginal profit in this example is 1, always increasing, 2, always decreasing, 3, increasing then decreasing, 4, decreasing then increasing, or 5, always the same. Okay, so pause the video for about 1 to 1.5 minutes and try this question. So 4, 3, 2, 1, pause the video. Pause the video for about a minute or a minute and a half to think about this and see if you can determine what the correct answer would be. Alright, so hopefully you've done that. Hopefully you've paused the video for about a minute to a minute and a half to think about this. So there are a couple ways we could determine this. So one is using the fact that the marginal profit function is p prime of x. So we could look at p prime of x. In this case, p prime of x is simple enough to graph. So we could look at the graph of p prime of x, which equals negative 0.004x plus 0.8. So we want to know whether this function, negative 0.004x plus 0.8, is increasing or decreasing or increasing then decreasing. Okay, but the graph of a line is easy enough to draw. If I draw some axes here, I can see the y-intercept of this line is 0.8, and it has a negative slope, but negative slope is really close to 0, so it's going to be a pretty flat line. So pretty flat line, maybe something like this. And this point right here, where the derivative equals 0, is 200. We found that already. P prime of 200 equals 0. We already found that. Okay, but looking at our derivative function, because that's what the marginal profit is. It's our derivative function. By looking at this, we see that this derivative, or marginal profit, is always decreasing. This is always going down. So the answer is 2. It is always decreasing. There's another way that we could have seen this by looking at the original graph, and I just want to sketch out that idea. So looking at the original graph, we need a way to be able to determine whether the marginal profit, aka the derivative, is increasing or decreasing, and if that changes. So if we look at different points on the graph and think about the slope of the tangent line, because that's what the derivative tells us. So if we were to look at a point like this, like this, and look at the tangent line, that tangent line has a positive slope. And if we draw more, if we draw a tangent line here, it's got a positive slope, but it's smaller. And if I draw another point a little bit further, now that has a negative slope, so it's smaller than the slope before, because before the slope was positive. And if I look at a point a little further down the road and draw its tangent line, that tangent line's slope is more negative, which means it's even smaller. So another way to see this is the slopes of the tangent lines keep getting smaller and smaller. And the slope of the tangent line, that's what the derivative tells us. So the derivative is always decreasing because the slopes of the tangent lines are always decreasing in this picture. So in terms of our goals for this section, we've now talked about how to use the derivative to determine when a function, like cost or revenue or profit, is increasing and when it's decreasing. In the next video, we'll define what the average cost function is.